Very good morning, everyone. And can you hear me? Yes. And thank you very much for this kind invitation. It's great to be here with all of you. I like very much the small workshops where we can interact better and better than big conference. This is really a great opportunity. And I would like to add to my talk, to my title, a motto that comes from a guru of spectroscopy who is Richard Crocombe. And the motto is shrinking, shrinking and shrinking, and spectroscopy in Wonderland. And this motto is inspired from the fairy tale of Alice in Wonderland. When Alice gets smaller and smaller, she can get into a magic garden, a magic world. And this is the same for spectroscopy. If you can do smaller and smaller and smaller devices, you will be enabled to have new opportunities, new applications. And it's not a fairy tale, it's reality, but this is just an inspiration. So a couple of words about myself. I'm coming from Italy, from Florence. Florence is the south of the north or the north of the south of Italy, depending on your perspectives. And this is the area of where my institute is. We are CNR. CNR is the National Research Council. It's not a university. We have very few students. And, but for funding, we compete at regional, national, and European level. And my institute is pretty big. We are more than 200 people, not only in photonics, also in space, aerospace, Earth observation, for health, nanomedicine, and safety. My group in food quality, but there are other people working in the environment section, and there are other people working for the cultural heritage. We are spectroscopists since, I would say, 30 years or more. We use the visible and near-infrared spectral range for absorption, reflection, fluorescence, also Raman excited at 1064, and we always combine spectroscopy with chemometrics. That is a multivariate data processing. To do what? To achieve a multi-component analysis. So the dream is to have a single spectroscopy measurements to have a multi-analyte sensing, provided that you have trained up the system, as I'm going to show you. We started with spectroscopy long ago for the environment, and this is a setting of water quality monitoring that we did around the 2000, where we installed spectrometers and optical fiber probes to measure the cleaning of the water during the entire process. And this is another industrial application that we did long ago in big machineries where tons of lubricant oils are used, and the aging of lubricant oil is very important to monitor because it is extremely expensive. And also in this case, not only the visible spectrum can give you an idea of how the lubricant oil ages, but also the near-infrared spectrum is very informative. Then we started with, let's say, food, when we worked in a European project together with Sandeman for port wine, and here we measure the color and the turbidity of port wine. And this is why we started with food, which is now our main activity. Which is our dream? Our dream is to use just one shot of light, make some data processing, shine light, get the spectrum, use mathematics to achieve a multi-component analysis for quality, authenticity, and also safety indicators, but mainly quality and authenticity, because for safety indicators, the levels are very little, and simply by spectroscopy is not easy to achieve. The advantage of using just spectroscopy without any chemicals, okay, there are disadvantages related to sensitivity and maybe selectivity also, but the advantage is that you are not using chemicals, so you do not discharge anything, so it is sustainable from the point of view of environment. Food is naturally colored. The beauty of food is the color. And from the color itself, you can get a lot of information about quality. Phenols are blue or violet, carotenoids are orange and red, chlorophylls are green. So simply measuring the color of food, you can achieve a lot of quality information. But the real interesting band is the near infrared, up to 2500 nanometers, because in this band there are the overtones and combination of overtones of these bonds. And these bonds are, I'm sorry that there is something that is misaligned, but anyway, in this band, this band is informative for proteins, carbohydrates, oils, water, cellulose, and sugars. Very important for sugars. So I'm mainly, at the moment, we are mainly focusing on the near infrared, not because the visible is not enough informative, but because it is better to go to longer wavelengths. And the problem of making just spectroscopy is that every component has the own absorption or reflection spectrum. And what you actually measure is the sum of everything. So in practice, you have a fingerprint, but you have lack of selectivity. This is why you always need some mathematics to get rid of that. Now, if you ask me which is the best mathematics, I cannot tell you. Okay, the best mathematics is the one that works for you. Okay? Now we are in the area of artificial intelligence. Everything is artificial intelligence, machine learning, neural networks, whatever you want to add is fine. We are expert in chemometrics. And chemometrics is a very subtopic of the artificial intelligence. But we are expert in chemometrics since more than 20 years, so we stay with that. Although probably there can be other better mathematics, but that is very basic, very simple. And never forget that from the data, you always can get what you are looking for, okay? Steering the data, the rabbit comes out. But never force, I tell you especially to the young generation, never force your data. And remember that garbage in, garbage out. Okay? If it is for a publication, it's okay. Everyone is looking for a publication, so steer the data until you get something reasonable. I think it's the same. I see Jean that agrees with me. Maybe it is the same also when you are processing your data, okay? But always make a verification of the data. Do not just steer the data until you get the results that you're looking for. Pay attention very much to use basic processing. That doesn't mean that you do not process the data. You process the data, I would say honestly, having in mind the ethics of a scientist. So what we do? We usually start with a collection of reference samples. And we take the spectrum, okay? Simply by taking the spectrum with a completely unsupervised method, you can make qualitative investigation, class identification with thresholds for authentication. So in this case, you do not need any reference data, but you can get only qualitative information from the spectrum. But if you go further, and if you have the reference data, the analytical data of what you're looking for, you can create a model, a predictive model, and you can do a quantitative analysis for the concentration detection, even for multi-component analysis. Pay attention that if your model is this, it means if your, the prediction with respect to the real values gives gives a regression coefficient equal to 1 with very little noise, okay, it means that the model is good. But if you are in this case, and this can happen, it means that the model is not very good, or at least it's not perfectly 100% good. The very important is to have the regression coefficient equal to 1, and as long as the regression coefficient goes less than 1, it means that your model doesn't work much. That's nature. In some cases, it can work. In some other cases, it cannot work. But always, always pay attention and do a validation phase. Validation phase means taking unknown samples, getting the spectrum, putting the spectrum in your model, and see to what extent you get the result, okay? So the validation phase is equally important than the calibration. Just to be sure that we are on the same page, what I'm going to show you from now onwards are a series of spectra, then a classification, and then a regression calibration. And this is the only formula I'm using, but once you have calibrated the system, it means that for every unknown sample, you get the value of the spectral data, and you put your value, the measured value, inside the formula, and then you add the regression coefficients and also the mean value of the spectral data from the calibration to have the concentration of the analyte that you're looking for, provided that you have calibrated carefully your system. Now, I think I'm the oldest in this room, and I'm very happy that I started with big spectrophotometers, benchtop. Maybe there are some in our laboratories. For sure you have seen this, and for sure you're still using, okay? These are excellent. These are excellent machines with excellent optics, grating, sources, and excellent. But they are benchtop. They are not very much practical to use online, to use on site, and they are also very expensive. Since the 2000s, thanks to the availability of small spectrometers and small sources, it was possible to create much smaller, much compact setup, okay? And after the 2010, these devices became even smaller and handheld. Now, the question is, since there are in Scopus, only looking at the title, 17,000 records related to the near-infrared spectroscopy, and not only to the near-infrared spectroscopy. And since this curve is getting steeper and steeper, looking at the very last years, the question is, can we do something with a mobile phone? Because everyone has a mobile phone in the pocket, even two. So that could be really an analytical lab in your pocket. Although this is working in the visible spectral range, but very soon, believe me, that will be available also in the near-infrared spectral range, because there are companies working in that, and because the consumer electronics is waiting for something to extend the range. So the question is, can we do an analytical lab in the pocket? Okay. The mobile phone has a source. It is a LED. It has a camera. The camera has 3 channels. RGB are 3 channels. And these 3 channels are not even independent. So in practice, you have only 3 numbers to use in spectroscopy. And 3 numbers that are not really 3 numbers. They are mixed. So in this case, you can do colorimetry, poor colorimetry, RGB colorimetry. This is something that we did in our lab to test what happens if you clip on a grating on the camera. Things are improving, okay? This is a grating that you can buy from a French company, it's a Go Spectro by, can't remember the name, I tell you later. from Goya Lab. Okay. And the colorimetry gets better, a bit better. This is the difference of colorimetry that you can get simply by an RGB and with a grating on the camera. So as an average, the difference gets from 34 simply with RGB to 29 with the grating as an average. And this number should be less than 10 to be acceptable. So still, with a grating on a camera, you have a poor spectroscopic resolution. There are other solutions that have been proposed in the literature. This is, for example, a sliding grating that is compatible with the cover. It means that the cover has a grating that you can use when you want to operate a colorimetry. But to my opinion, this is not practical because the models of smartphones are changing every week, every month, every 6 months, you have a new model. So what you design for a certain model, suddenly it becomes old. So to my opinion, this is not the way of doing. Although these things are working, have been proposed and sold, so they can be a good option. Other colleagues decided to clip on something, to clip on some small laboratories, okay? And also these are very nice solutions. This is from a colleague in the Philippines, and this is very nice. It is a little laboratory that exploits the use of the camera and of the light. And there are also other examples, more complicated, where as a cover, the cover is itself a lab. This is an old paper that has been proposed, but is still very much valid. And you can see that the cover has additional light, additional battery, additional optical component, but the story is the same. What you do now let's say for an iPhone, which is one of the most used telephone, or for one of the Samsung telephone, maybe in 6 months it's no longer used. So you do something, invest a lot of money, a lot of time to do spectroscopy, a pocket-sized spectroscopy with a very nice lab, but it is in practice, it gets old instantly. Or not instantly, but very soon. So while we are waiting to see the spectrometers integrated in the smartphone, okay, while we are waiting for that, a good solution can be using Bluetooth-connected devices and using the smartphone as a hub for these devices. So you are connected with a pocket-sized, I'm going to show you, a pocket-sized device, and you use the smartphone as a hub to operate the pocket-sized device, to get the data, to send to the cloud the data. So in practice, a very, very straightforward way of having a pocket-sized analytical lab is to have something small, Bluetooth connected with your smartphone, get the data are going to the cloud, they are processed by the cloud because the mobile phone itself does not have the processing capability. And from the cloud, the data are sent back to the mobile phone. So this is something in between, waiting to see spectrometers really integrated into smartphones. Now, there are plenty of small spectrometers and spectral sensors in the market. I'm sure that I forgot to mention some of them. And if you want to read a very nice review in food spectroscopy, this is something that I liked much. If you want to read a very nice review about near-infrared spectroscopy with pocket-sized devices, also this is a nice review to read. In my lab, we had to take a decision what to use. We cannot test them all and make comparison and benchmark. And we decided to use the SIO. This was, I think, the first spectral sensor Bluetooth connected to the mobile phone that appeared on the market. And this is another one, SpectraPod, by a company in the Netherlands that we decided to buy. And we are starting also doing tests with this new one. This is the first that appeared on the market. It is from an American company. The name is Telspec, and inside this device, there is a real little spectrometer, okay? Look at the size. This is made by Texas, and it is integrated into this, and inside this, there is the battery, there is the Bluetooth connection, and all the apps to achieve optical spectroscopy and qualitative information. But this is a spectrometer, okay? So the size, you see here, this was a concept that never appeared. This is much bigger, is this size. So it's still not much pocket sizes. So we wanted to pass to spectral sensing, multispectral sensing, which is different than using a grating. When you use a grating, you see a spectrum, okay, with a certain resolution. If you use a spectral sensor, it means that on top of your detectors, you put filters, and it means that you slice the spectrum into different slices, and for every slice, you have the integral value. So in practice, you have a series of pixels. It's like having an optical nose. The concept is nearly the same. We like it very much, this solution, because it is less expensive and you can create smaller devices. This is the system that we are currently using. We followed up the development since its very beginning because we were in contact with the consumer physics company that is producing this device. It is this one. Okay, clear? And this is the chip. This is the LED here, and this is the detector. And the detector is made of a CMOS detector with a series of 12 filters on top. There is also a mask for equalizing the signal and also lenses for a better light coupling. The reason why we like it so much, this device, is not because it was one of the first, and because really it's amazing. The data that are sent to the cloud are reconstructed. What you get a reconstructed spectrum, which is really nice to work with. They are selling this device even in a miniaturized shape. And they are selling, the company is selling compatible with a cap or compatible with other holders because they have identified for their business and for their venture capitalists to measure, for example, the dry matter in animal feeds or to measure the moisture contents in corn or in grains. But they also have apps for measuring the sugar of berries and for measuring the fats and other properties of the dairy products. But there is an option that if you pay every year the connection to the cloud, and this is the bottleneck of this device actually, you can use it as a developer and as researcher. So you can get the data that you measure from the cloud, you can process on your own or through the cloud. And this is a very flexible way of doing that we do actually. These are papers that have been published, but there are many more. There are more than 100 papers published using this SIO device. This means that it is really getting reliable, because if a lot of scientists demonstrate the effectiveness, it means that this kind of device can get into a practical use. We have used for olive oil. and not only, but we started using for olive oil. These are the transmission spectrum of olive oil in the entire band from the ultraviolet to 2800 nanometers, okay? Look at how rich it is. In the visible, there is the color of the olive oil that is always different. And in the near infrared, there is information on fatty acids. But with the SII device, we can investigate only this small band. Okay, so it's modest in comparison to the entire information that you can get, but it's still effective. And I'm going to show you our example. We had a project together with the company Consumer Physics, and we tested different oils of different years. Some of them were extra virgin, some others were very low quality. These are typical spectra that we get in transmission with putting the oil inside vials and having a very small holder that we printed with a 3D printer. So very easy and low and cheap. And as a first exercise, we wanted to check if it is possible to detect extra virgin olive oil from non-extra virgin olive oil. And actually, this was possible. You see the accuracy is very good in calibration and still very good also in validation. But this was just an exercise. The company that we worked with actually was interested to put this teeny tiny device at the end of the mill to check the fatty acid profile, because the fatty acids are mentioned in the label, and it would be good to have an idea if the process of the mill is going well to achieve the fatty acid profile, the ideal fatty acid profile. As fatty acid profile, PUFA means polyunsaturated fatty acids, and it is the sum of linoleic and linolenic acids that are the famous omega-3 and omega-6, very good for the health, antioxidant, and blah, blah, blah. The other fatty acids are MUFA, monounsaturated fatty acids, and the other are the saturated fatty acids that are palmitic and stearic, that are not good for the health. These are the results of our training. I told you that when the regression coefficient is close to 1, it means that the model is going well. And in this case, for the polyunsaturated fatty acids that are the omega-3 and omega-6, the model was great. It was reasonably good, nearly 0.9, also for monounsaturated fatty acid, and it was still acceptable for saturated fatty acid. For saturated fatty acids is not great, but we can still put thresholds to decide whether the product is acceptable or not. Another application for olive oil is to measure the water content that remains in the oil, because olives are washed. I'm sorry that there is something that is my writing is misaligned, but anyway, no matter. And we were able to measure the percentage of water at the end of the meal with a threshold of 0.05 in volume, okay? This is a very low threshold, and we were very good both in calibration and validation with 97%. So all these, the blue, have low value of water. This is an error that accounts for this 97% rather than 100%. You do not hear me. Okay. And the red ones are the samples with a concentration of water higher than 0.05%.
So what's the matter of noise? Projecting noise is
Another application that we can have still in the olive oil world is to measure the hydration of the leaves. The hydration of the leaves to decide if the plant has a water stress or not. These are the concentration of water of a series. We did many measurements during from 2022 to 2023, many sampling, many different trees. And these are, for example, I'm sorry, there is something missing. The idea is to have eventually an app that tells you whether the tree needs water or not. Water is very expensive. I think that also here in Spain, watering is a problem because water is scarce, okay? Time, okay. So these are the tests that we run, and we put a threshold to decide whether the plant needed watering or not. And these are very good results that we achieved with the spectra, with water higher and lower than 50%, and these are the classification and the regression coefficient. So also this is an application that can go thanks to this device, Bluetooth connected, and an app. Now, I'm running because time is getting short. This is another application in tomato plant where we were able to detect the fungi onset. You see that this part is safe, the other part is infected by fungi. But from the outside, you were not able to detect it. The near-infrared penetrates and can give you this kind of information. We are working in this limited band, but in spite of that, we were able to classify correctly with an accuracy better than 90%. Running, another application is to detect the botanic origin of honey. Honey is terribly expensive, and it is also nice to know which kind of botanic origin it is, and these are the classification map for distinguishing chestnut, citrus, and eucalyptus honey. And another application is for fraud detection, for example, of carob molasses. Carob molasses are very typical in Lebanon. We had a guest from Lebanon that wanted to see to what extent it is possible to detect the fraud caused by sugar and sugar made of sucrose and fructose. These are the spectra of sucrose and fructose. These are the spectra of carob molasses. And when we mix and we create adulteration, we get mixed spectra. And if we process the spectra, what we get is really a very good results of detecting the fraud with 0.9 in calibration and also in validation. So also for authenticity detection, for authenticity purposes. The other that we are experimenting is the SpectraPod. It has 16 channels in the wide range from 850 to 1700 nanometers, and it means that in this case we do not get the spectrum, we simply get the pixel. And we have tested in flowers, different types of flowers made of cereals, legumes, tubers, and many others, and we were able to, this is what we did, we were able to classify carbohydrates and proteins in low or high content. So this comes now as, I saw it recently at Photonics West, that this device was coupled to a mobile phone by StellarNet. StellarNet is a spin-off company by NASA. Although I don't like the use of coupling spectrometers to the cover, this is something that I like particularly, and eventually we are waiting to see these devices integrated into mobile phones. There is the consumer electronics that is pushing towards this direction, and very soon we will see them. I finished, and these are other spectrometers. I think these are dreams of spectrometers integrated into a case of a smartwatch. And this is very useful also for agriculture. And if you want to see how photonics is good for the agri-food world, please have a look to this recent roadmap that we co-edited with other 2 colleagues, all women, to support the women in sensors. And if you have companies interested to see to what extent photonics can find an answer to their questions, please come to the European hub, Photon Hub, that now became Photon Factory. And for sure, there will be photonic solutions to many questions of many companies. Thank you very much for your attention. I'm sorry I was late. And
thank you, Anna, for your time.
I hope to have collaborations, whatever collaboration you have in mind. I see that there is a IS food here, so we might start thinking, working together. And later on, I can show you a demo of this little device with an Apple or with something, so you can figure out how it works. Thank you very much.
Thank you very
indeed.
much.